Welcome to the introduction of the Advanced Computer Graphics course. My name is Matthias Teschner and I am Professor for Computer Graphics at the University of Freiburg. Computer graphics is an area of computer science that is comprised of different areas. Three of the major areas within graphics are modeling, rendering, and simulation. And in the introductory graphics course, I've already discussed various aspects of these three areas. Now here in this course, we focus on rendering or the synthesis of images. So based on the geometry of a scene and based on the reflection properties of the surfaces in a scene, we look into the question how to compute the light transport from the scene towards the sensor as accurate as possible, but also as efficient as possible. In the introductory graphics course, I've already discussed some basics in the context of rendering, mostly in a rather informal way. Now here in this course, we look into all relevant rendering aspects in a more formal way. We will see how to use actual radiometric quantities to describe light. We will discuss the integral equation that governs the interaction of light with surfaces, and we will look into concepts for solving the integral equation. Now here in this introduction, I will try to explain the general problem that we have to solve when rendering an accurate image, and I will introduce some general ideas to solve the problem. And of course, I will also talk about organizational aspects. Now here we have the outline of this introduction. I will start with organizational aspects, and then I'm going to introduce various concepts that are relevant for the rendering of images. I also show some application areas where computer-generated images are relevant, and I discuss some of the historic developments in rendering with a focus on the evolution of the employed concepts. So let's start with organizational aspects. This slide summarizes our teaching activities. First of all, we offer a general introduction to computer graphics. This introduction is part of the key course Image Processing and Computer Graphics, where the introduction to graphics is combined with an introduction to image processing. In the graphics part of this course, we talk about selected aspects of modeling, rendering, and simulation, with a main focus on rendering. In addition to the key course, we offer two specialization courses. One specialization course is concerned with rendering, the other one focuses on simulation. In the simulation course, we are concerned with concepts to simulate deformable objects, rigid solids or fluids, and therefore we mainly look into particle-based approaches. Now here in the advanced computer graphics course, we look into so-called global illumination approaches, for instance radiosity or stochastic ray tracing. In order to realize photorealistic images, it's important to capture all light transport in a scene. So surfaces are not only illuminated by light sources, but surfaces also illuminate each other. And such effects are captured by global illumination approaches such as radiosity or stochastic ray tracing, and in this course we focus on such global illumination approaches. In addition to these courses, we also offer seminars, an animation seminar and a rendering seminar, and we also offer all types of projects and theses. We offer bachelor projects, master projects, lab courses, bachelor and master theses. In terms of the projects and thesis, we distinguish two tracks, a simulation track and a rendering track. When interested in graphics at the University of Freiburg, you can either focus on simulation or on rendering. So if you are more interested in simulation, you can start with the simulation course in the winter term. In the following summer term, you could attend the key course on graphics. The key course and the simulation course are rather independent. The key course has a strong focus on rendering, so it's not necessarily a prerequisite for the simulation course. In the summer term, you could also do your lab course or attend the simulation seminar. Then in the following semester, you could continue with the master project and then finally write your master thesis. In the rendering track, you could start with the key course in the summer term, and then you could attend the advanced rendering course in the following winter term. In parallel, you could also participate in a lab course and in a master project. Of course, you could also attend the rendering and the simulation seminars. Again, the track would be completed with a master thesis. I find it particularly important to thoroughly plan the projects and the thesis. On one hand, one could do the lab course, the master project, and the master thesis in different areas of computer science. The question, however, is whether this makes sense. I would actually argue that it's better to do the lab course, the master project, and the master thesis in the same area. In this case, the master thesis can be built upon the results of previous projects. This is illustrated here for both tracks. In the simulation track, for instance, one could implement a simple fluid solver in the lab course. This simple fluid solver could be extended or improved in the master project. For instance, the data structures for the neighbor search could be improved, or the pressure computation could be improved by incorporating a so-called PPE solver, where PPE stands for pressure-Poisson equation. Based on the results of the master project, it would be possible to write a master thesis that addresses very interesting, challenging, and relevant aspects in fluid simulation. So in the master thesis, it would be possible to focus on a research-oriented topic. The same holds for the rendering track. In the lab course, you could start with a simple ray tracer. In the master project, this ray tracer could be extended to a sophisticated stochastic ray tracer that employs Monte Carlo integration, and the data structures for the ray traversal could be improved. Then the outcome of such a project can be the basis for a highly interesting rendering topic that is covered in the master thesis. Now let's get back to this course and its goals. The main goal of the course is an introduction to various concepts that are used in the synthesis of images. The techniques that we look at are also sometimes called global illumination approaches, which refers to the fact that the concepts try to compute the entire light transport in a scene as accurate as possible. In contrast to simple rendering approaches that only consider illumination from light sources, global approaches also consider illumination that results from the reflection of light from other surfaces. We will see how to model the light transport in a scene, and in particular how to model the interaction of light at surfaces with a governing equation, the so-called rendering equation. And we will discuss concepts to solve the governing equation to reconstruct the light transport in a scene. In particular, we will look into these topics. I will introduce radiometric terms that are used to quantify light. We will discuss the rendering equation that governs the light interaction at surfaces, and we will talk about radiosity and ray tracing, which are two concepts to reconstruct the light transport in a scene, which in turn is the basis for the rendering of an image. There exists a variety of variants for both concepts. In terms of radiosity, we just look into the general idea. This idea is actually relevant to get an improved intuition of why ray tracing actually works. And in terms of ray tracing, we focus on so-called Monte Carlo techniques, which refers to the fact that Monte Carlo integration is used to approximately solve the integral in the rendering equation. I do not expect specific knowledge to follow this course. Nevertheless, it makes sense to first attend our introductory course, where I already introduced some rendering aspects. In particular, some knowledge about ray casting and about the Phong illumination model would be helpful. Regarding the material for the course, you can find all slide sets and video recordings of all lectures on our webpage that is indicated here. On our general webpage, there's a link to our teaching webpage, and on this teaching webpage, you can find all material for all of our courses. In terms of related literature, I do not recommend one specific book, but instead there exist various books that might be of interest for you in addition to the slide sets. The first book that I'd like to recommend is Physically Based Rendering from Matt Farr and colleagues. This book covers a large number of topics that are relevant in rendering. It covers basics, it covers concepts, and it also discusses implementation aspects. It has a focus on ray tracing and covers recent developments in that research area. The book is available online for free. The second book is Ray Tracing from the Ground Up by Kevin Suffern. Compared to the PBR book, this book focuses more on practical aspects. Here we have two more books. Advanced Global Illumination by Phil Ducherry and colleagues covers the theory of many relevant concepts in a very comprehensible but also compact way, while Peter Shirley's realistic ray tracing is a compact mixture of theoretical and practical aspects of the original ray tracing concept. The last book I'd like to recommend is an older one, Principles of Digital Image Synthesis from Andrew Glasner. This book is from the 90s and has about 1200 pages and is available online for free. In contrast to my other recommendations, it covers more topics. In particular, it covers signal processing aspects, and in terms of rendering approaches, it's not limited to ray tracing, but it also explains religiosity. In addition to the lectures, there will also be exercises. The exercises focus on the development of some basic ray tracing functionality, and the respective information can be found on our teaching webpage. In particular, we provide example frameworks that could be used. But of course, you are free to choose whether to work with an existing framework or whether to build your own ray tracer from scratch. The exercises are not mandatory, but if you are interested in a rendering project in the following semester, the exercises are of course recommended. At the end of the course, there will be a written exam. The respective questions are related to the slide sets and the lecture recordings. And towards the end of this course, I will also summarize the material that is relevant for the exam. That's it about organizational aspects. Now in the following part of this presentation, I'm gonna introduce some aspects that are relevant in the rendering of images. The most basic aspect that is relevant in image synthesis is the modeling of light. In our graphics world, light consists of photons, which can be seen as small energy parcels. These photons move along straight lines at infinite speed. Later in this course, we will see that the intensity and also the color of light that moves along a certain line can be expressed with the radiance L, which is a radiometric quantity. The term infinite speed refers to the fact that we are not interested in simulating the actual movement of photons. Instead, in image synthesis, we compute equilibrium states. We are typically interested in computing the number of photons within a given time frame that hit a certain area of a sensor. Light is generated and emitted by light sources. At surfaces, incoming light is scattered or absorbed. This process is governed by the rendering equation. In participating media, light can be scattered or absorbed as governed by the volume rendering equation, and then finally light is absorbed by a sensor. The sensor data is post-processed and then we finally get the final image. Now this slide illustrates these aspects. First of all, light moves along straight lines. At any point in space, there's incoming and outgoing light into all directions. Next, light is generated by light sources, as indicated here in this illustration. Now at surfaces, we have some light interaction. Dependent on the reflection properties of the surface, light is partially scattered and partially absorbed. Here, for instance, we have a green surface. The black arrow indicates some incoming light, and the gray arrows indicate the amount of reflected light into the respective directions. The actual reflection pattern depends on the surface material. If the surface is dark, less light is reflected. If it's bright, more light is reflected. Also, if the surface is matte, reflected light is scattered into many directions, while shiny surfaces reflect light in a more focused way. Light does not only interact with surfaces, but light also interacts with so-called participating media. So for instance, if light moves through fog, then fog absorbs and scatters light. These two interactions, the interaction with surfaces and the interaction with volumes, are governed by equations, namely the rendering equation and the volume rendering equation. Finally, we are interested in measuring the light that is absorbed by a sensor. This can be a camera or the human eye. The measured light, typically photons per time per area, is post-processed or interpreted by the human brain, and we get the final image. Photons are small energy parcels that are characterized by a wavelength within the visible spectrum. This basically means that each photon has a color. So here in this simplified illustration, we assume that photons can have 3 different colors. They can either be red, corresponding to a wavelength of lambda 1, they can be green, corresponding to lambda 2, or they can be blue with a wavelength of lambda 3. And now these photons can be mixed, and dependent on the distribution of wavelengths, we get colored light. If we have just red photons, then we get red light. If we have the same amount of red and green photons, but no blue photons, then we have yellow light. If we have the same amount of red, green and blue photons, then we get white light. So the distribution of wavelengths within the set of photons is interpreted as a color. So when we measure photons per time per area at a sensor, then we actually measure two aspects. We measure the intensity corresponding to the overall energy of the photons per time and area, and we also measure the color of the incoming photons by analyzing the distribution of wavelengths within the set of photons. Now in the following, I'd like to discuss the governing equations that describe how light interacts with surfaces and within volumes. So the rendering equation describes how light interacts with surfaces, and the volume rendering equation describes how light interacts with participating media when traveling through a volume. First we look into the rendering equation, and then we look into the volume rendering equation. So here we start with the rendering equation. The rendering equation describes how much light or radiance LO is reflected into a particular direction omega O given incoming light Li from all directions omega I, and also considering the reflection properties of the surface, which are represented by the function Fr. The setting is indicated on the left-hand side. We have a point position P on a surface, and we have incoming light Li at point P from direction omega I. And now the rendering equation states how to compute reflected light LO from position P into a direction omega O. In the illustration, the outgoing light is indicated with the gray arrow. Now in the rendering equation, we have the incoming light or radiance Li from direction omega I. This incoming light is multiplied with the cosine of an angle theta, which is the angle between the direction of the incoming light and the surface normal at position P. This multiplication accounts for the illumination effect of the incoming light onto the surface. So dependent on the direction of the incoming light, we end up with different illumination strengths at the surface. Light orthogonal to the surface has a larger effect on the illumination than, for instance, light that moves parallel to a surface. This concept is also referred to as Lambert's law. The surface illumination is then multiplied with the function Fr, the so-called bidirectional reflectance distribution function. This function models the behavior of the surface in terms of how much light is absorbed, how much light is reflected, and which amount of light is reflected into which direction. So in the integral, we consider Fr at position P for some incoming direction omega I and some outgoing direction omega O. So the respective function value states how much of the incoming light from direction omega I is reflected into the direction omega O. Now the entire term Fr times Li times cosine theta is integrated over the entire hemisphere. So for all directions omega I of the hemisphere, we accumulate the reflected light into the direction omega O. The entire equation is referred to as rendering equation, and it describes the interaction of light with surfaces. So basically based on incoming light Li from direction omega I and based on the surface reflection properties represented in the function Fr, one can compute reflected light Lo into a direction omega O. Light transport is not only affected by surfaces, but it's also affected within volumes in the presence of participating media. So here in this illustration, light travels through the points P and P1 along some line with direction omega. And here you can see four effects that occur when light moves through participating media. Two effects have positive contributions to the amount of light traveling along the line. Two effects have negative contributions. For instance, light can be absorbed between positions P and P1 as indicated by the respective equation, or light can be emitted. So you can subtract or add some light while moving from P to P1. And you can have in-scattering or out-scattering effects. Out-scattering means that light that has originally moved along the line changes its direction between P and P1. In-scattering means that light changes its direction from another path onto the line between P and P1. The governing equations are very powerful. They can be used to compute the entire light transport in a scene at each position into all directions. This is illustrated here in a simple 2D setting. We have a box with one blue object inside the box and some light source shown in red. Now, if we know how much light is generated at the light source into which direction, and if we know the reflection properties of all surface elements, then we can use the rendering equation to compute the entire light transport within this scene. In particular, we would consider the rendering equation at each surface element for all outgoing directions and then solve a system to simultaneously compute the entire light transport in the scene. The black line segments at the surfaces in the illustration represent the reflected light, and the computation of reflected light from all surface elements into all directions is the general goal of all rendering concepts. Of course, in practice, this computation is always approximate, but actually all rendering concepts try to capture the entire light transport in a scene as accurate as possible. Some concepts impose more simplifications and are more efficient. Others are more expensive but use less simplifications and are more accurate. Once we know the light transport in a scene, we can render an image of the scene. And if we know how much light is reflected from all surface elements into all directions, then the rendering process is just a lookup as indicated in this illustration. You can place a sensor at an arbitrary position with an arbitrary orientation looking into the scene, and then you cast rays into the scene for which you compute intersections with the surface elements. Then you look up the light that is transported along the ray from this intersection point to the sensor. So if the entire light transport in a scene is known, then the rendering is a simple lookup. The image on the right-hand side shows a rendering of a simple 3D scene. Again, the general goal is to compute the light transport from all surface points into all directions, and based on this information we cast rays from the sensor into the scene and look up the respective light values that comprise the image. So in general, all rendering algorithms are concerned with the computation of light transport in a scene. And here we always aim at computing the entire light transport in a scene as accurate as possible. If some light transport is omitted, this might potentially degrade the quality of the rendered image. In practice, however, it's never possible to entirely reconstruct the full light transport in a scene. So rendering approaches typically incorporate simplifications. And here there exist different strategies and we end up with different rendering concepts. One of the major rendering concepts is referred to as radiosity. Here we explicitly compute the full light transport according to the idea outlined in the previous slides. The goal is to compute the light transport as accurate as possible given some constraints. The first typical simplification would be the absence of participating media. In this case, light only interacts with surfaces but not within the entire volume. Another typical simplification would be the discretization of a scene into surface patches of finite size. So instead of computing the light interaction at an infinite number of surface points, we just compute the light interaction for a finite number of surface patches, for instance triangles. The third typically employed simplification is the assumption that all surfaces are perfect diffuse reflectors. In this case, light is equally reflected into all directions, and the amount of reflected light is independent from the direction. These assumptions result in the fact that we have to compute just one unknown for each surface patch to represent the entire light transport in a scene. So in the radiosity concept, we consider the rendering equation at each surface patch and end up with a linear system with one unknown reflected light value for each surface patch. Once the light transport is computed, images can be rendered for arbitrary camera settings. The name radiosity stems from the fact that the concept actually computes the overall amount of reflected light from a surface patch. This value is a radiometric quantity named radiosity. The second major concept is ray tracing. Here we select specific line segments or rays for which we compute the light transport as accurate as possible. In the illustration we see some selected line segments. The red ones connect the sensor with the scene and are typically referred to as viewing rays. These rays are required for all sensor elements to compute the captured light at each sensor element. The goal is to compute the light transport from the scene towards the sensor along such viewing rays. At the intersections of viewing rays with the scene, we evaluate the rendering equation. Based on the illumination of the intersection point, we compute the light that is reflected towards the sensor. Now, in order to capture the illumination from the light sources, we consider so-called shadow rays, and we compute the light transport from a light source to the intersection of a viewing ray with the scene. This is actually a minimal setup. Without the viewing rays, we could not compute the light transport to the sensor, and without shadow rays, the illumination of the scene from the light sources would not be considered, and we would get a black image. It's obvious that viewing and shadow rays are certainly the most important line segments in a scene for which we have to compute the light transport. However, scene elements are not only illuminated by light sources, but also by reflected light from other surfaces. So in order to get more accurate images, a ray tracer has to incorporate more and more rays or line segments or connections in a scene. And now there exist numerous strategies to find and incorporate relevant rays into the computation. Typically, one is interested in rays where more light is transported, while rays with less light transport are less relevant for the image quality. In general, however, ray-traced images get more and more accurate with a growing number of rays that are considered in the computation. Here we have a 2D illustration of the ray tracing concept to illustrate its simplicity but also its challenges. We have a scene with two surface patches P and Q, a light source and a sensor. Now, the main goal of the ray tracer is the computation of the light transport along path number 4 from point P into the direction of the camera. Path 4 would be a viewing ray. In a minimal setting, we would just consider the illumination from the light source. So we need to compute or look up the light transport along path 2 from the light source towards surface patch P. With this information, we can evaluate the rendering equation at P in order to compute the light transport along path 4. In order to improve the image quality, we could also consider the illumination of point P that results from reflected light from point Q along path 3. In order to compute this light transport, we would look up the light transport along path 1 from the light source to point Q, and we would evaluate the rendering equation at point Q. If there would be more surface patches in a scene, we would need to incorporate more and more rays to consider all illuminations from other surface patches. Another important challenge is the fact that the surface patches illuminate each other. So Q illuminates P, but P also illuminates Q. So either we solve a system, as we do in the radiosity concept, or we iteratively improve the image quality by going forth and back between two surface patches in a ray tracer. So the illumination from Q influences the reflection at P. The reflection at P towards Q updates the information of Q, which influences the reflection from Q towards P, and so on. So on one hand, the ray tracing idea is simplistic. On the other hand, ray tracing can be involved when we try to capture more and more light transport in a scene in order to get an accurate image. So, which aspects are important when we try to render an accurate image? First of all, we need accurate models for the light transport. For instance, we need to model how light interacts with surfaces, which is realized by the rendering equation. Another highly relevant aspect is a realistic parametrization of our scene elements. For instance, if we render a perfect red sphere under a point light source, then the resulting image will never look realistic, no matter how accurate we compute the light transport. This is due to the fact that in reality we do not have perfect materials and we do not have point light sources. So we can never observe such a scenario in reality, and the respective rendering would always look unrealistic. So a realistic parametrization of the geometry and of the reflectance properties in a scene is highly important. When we have appropriate models and appropriate parametrizations, then we can get realistic renderings by computing the light transport for as many line segments or rays in a scene as possible. The more rays we consider in our computation, the better the image gets. As our computing resources are always limited, we typically cannot compute the entire light transport in a scene. We need to choose rays that are more relevant to our rendering result, and we try to omit rays that are less relevant. Here exist numerous strategies to choose relevant rays, and the investigation of such strategies is addressed in research. One rather obvious criterion for the classification of the relevance of rays would be the amount of light that is transported along a ray, which is referred to as radiance. So rays with larger radiance are potentially more interesting and relevant compared to rays where less radiance is transported. One of the parameterization aspects is illustrated here in this slide, namely the illumination setting. Realistic illumination settings are an important basis for realistic images. In the illustrations, we have three examples of the same scene with different illuminations: daylight, at night, with and without additional lamps. So typically we have complex illumination settings, and only if these settings are modeled appropriately, then we are able to render realistic images. Or the other way around, if the illumination setting is simplistic, then we do not get realistic looking images, no matter how good or bad the rendering concept would be. The same argumentation holds for the parametrization of the reflection properties of the surfaces in a scene. Only if the material properties are adequately represented, then we have the chance to get realistic looking images. If the material setting is too simplistic, then the image will never look realistic. If the parametrization is adequate, then we have the basis to generate realistic images. And in order to do so, we always aim at computing the entire light transport in a scene as accurate as possible. The more rays we consider, the better the image gets. But due to limited computing resources, we generally incorporate simplifications in the light transport computation. For instance, we discretize the surfaces into finite size patches, or we try to identify rays or line segments whose light transport is more relevant to an image, and we try to neglect rays that are less relevant. That's it about the introduction to some of the concepts that we will address in this course. In particular, we will see how to model light with radiometric quantities, how to describe the light interaction at surfaces with the rendering equation, and how to approximately solve the rendering equation with rendering approaches such as radiosity and ray tracing. Now in the following, I will briefly outline some application areas where the rendering of images is relevant. So here I discuss some selected application areas. First of all, computer-generated images are generally of high relevance in movies and commercials. Dependent on the scenario, sequences are either entirely or mostly computer-generated. Of course, the extent of using computer-generated images differs, but in architecture or in automotive scenarios, they are used frequently and extensively. In other settings, such as flight and car simulators or in computer games, it's rather obvious that those scenarios entirely rely on computer-generated renderings. Here we have an example on how photorealistic renderings are being used in the context of architectural design. High-quality rendering enables the visualization of a design in certain illumination settings. And visualizations can be generated for different illumination settings. So one can visualize a building under a cloudy sky or in bright sunshine. The same holds for the rendering of interior scenes. Here, the illumination due to windows or lamps can be specified by a user or customer, which allows to assess a design under varying conditions. Also, materials or colors can be easily adapted in a virtual scene, which would be much more involved when taking photographs of a real setting. Similar motivations hold for other application areas, such as automotive design. Here, photorealistic renderings are used, for instance, in so-called car configurators, where customers can choose colors and materials of the car interior. Or renderings are being used for illustration purposes of certain parts of a car, or renderings of the entire car are being used in ads and commercials. Again, the motivations for working with computer-generated images are versatility and efficiency. On the left-hand side, you see an illustration of the geometric representation that is used for the photorealistic rendering shown on the right-hand side. You can imagine that such a setting provides a lot of flexibility, as many aspects in the scene can be user-defined. The environment, the weather, the time of day, and of course all materials and colors related to the car itself. Again, compared to taking photos in a real scenario, virtual scenarios are highly flexible and can be efficiently rendered several times for different parameterizations. Also, dynamic aspects are often computer-generated. Here we have an example of simulated rain, where the simulation is illustrated on the left-hand side and a still image of the final video sequence can be seen on the right-hand side. The pre-processing for a computer-generated video sequence is certainly expensive, but once the environment is set up, a variety of aspects can be adapted according to the requirements and preferences of a customer. This last illustration in the context of automotive applications should highlight the fact that computer-generated photorealistic images can also be combined with real videos. So for instance, you can film an actor and combine this with a computer-generated sequence. I hope I could convince you that photorealistic rendering approaches are relevant in a variety of application areas. Now, in the next part of this presentation, I'd like to highlight a few historical aspects in the evolution of rendering concepts. In this discussion, I'd like to focus on two of the major rendering concepts, namely rasterization and ray tracing. And here on this slide, we start with rasterization. The development started in the 60s, and one of the first topics that had been addressed was the projection of primitives onto the viewplane. Bresenham developed algorithms to project lines and circles onto the viewplane, and also the projection of polygons had been investigated. Then the Phong illumination model was proposed. This model describes the interaction of light with surfaces in case of diffuse and specular reflection, and it is important to estimate the light transport from visible scene elements towards the sensor. Another important development was the depth buffer concept that is used to resolve visibility in a scene in a very elegant, efficient, and parallelizable way. Then, on top of the development of these basic rendering functionalities, people started to investigate the incorporation of additional visual effects. One example in this context are shadows. Here, Crow proposed shadow volumes and Williams proposed shadow maps to distinguish illuminated surfaces from shadowed surfaces in a scene. Shadow volumes use additional data structures, while shadow maps rely on multiple rendering passes. It is interesting to note that rasterization approaches have largely focused on the light transport along viewing rays. And the basic algorithms for resolving visibility and also for computing the transported light towards the viewer are well established and typically perfectly parallelizable. That's why rasterization approaches have been hardware supported from early on, and that's why rasterization approaches are popular in interactive applications. On the other hand, rasterization techniques are difficult to handle when it comes to complex visual effects. As nicely illustrated by the shadow techniques, specialized methods have to be realized that either use additional data structures or additional rendering passes. And this is actually an important difference to ray tracing algorithms, where everything is based on a unified concept, namely the computation of the light transport along rays. If one would like to realize additional visual effects, it's sufficient to just consider more rays. Now here I'd like to discuss a few important steps in the development of ray tracing. This development also started in the 60s, parallel to the development of the rasterization concept. One of the first variants had been referred to as ray casting. Here viewing rays and also shadow rays had been used. Viewing rays resolve the visibility problem, and shadow rays allowed to distinguish shadowed from illuminated surfaces. As a next step, recursive ray tracing had been proposed. Here additional rays are considered at intersection points between viewing rays and the scene. In particular, so-called reflection and refraction rays had been considered, which allowed to incorporate the ability to render mirroring surfaces and transparent objects. Again, this is an example that additional visual effects can be uniformly realized by incorporating additional light transport in a scene. Another very important aspect in the development of ray tracing approaches was the proposal of the rendering equation as a governing equation that models the light interaction at surfaces. The rendering equation is an integral equation, and in the following years, methods for solving this equation have been investigated. And here, Monte Carlo integration is a highly popular technique to solve the integral in the rendering equation. Up till now, Monte Carlo variants are investigated in graphics research to improve the accuracy and the efficiency of this integration scheme applied to the rendering equation. It started with path tracing in 1986, and still today, graphics research focuses on the investigation of appropriate sampling strategies. Which rays should be considered, which rays are less relevant, and how to efficiently estimate sets of rays that are adequate to realize a specific visual effect. Again, ray tracing bases on the idea of uniformly considering rays to capture visual effects in a rendering, while rasterization typically requires specialized solutions for different effects. That's why ray tracing is more popular in the context of high-quality, photorealistic image generation. Ray casting and rasterization differ in terms of pros and cons, but nevertheless they basically solve the same problem as indicated in these illustrations. For a point P in a scene, both concepts find the projected position Q on the view plane. In order to do so, ray casting traces a ray into the scene, while rasterizers perform a transformation to compute the projected position. So both concepts can be used to solve the visibility problem, and then the light transport from the scene point P to its projected position Q has to be computed. If ray casting is extended to recursive ray tracing, then we consider additional rays that start at scene point P. And this is what makes the ray tracing concept generally more suitable for complex visual effects. One always works with rays, while in rasterization, different concepts have to be combined. The discussion of ray tracing versus rasterization is summarized here on this slide. Ray tracing has the advantage or nice property that potentially the entire light transport in a scene can be computed by tracing rays. This allows for a natural incorporation of more or less arbitrary visual effects by just considering additional rays in the rendering process. Of course, the computations get more and more expensive, and there's an obvious trade-off between quality and performance. Now in rasterization, there's a clear focus on the light transport along viewing rays. By applying the projection transform in the rendering pipeline, we basically establish viewing rays. If we are interested in any other light transport in the scene, for instance shadow rays, then we need specialized realizations. On the other hand, rasterization algorithms are well established, typically parallelizable in a perfect way, and therefore conveniently realizable in hardware. This is what makes them popular in interactive applications. Now in the following slides, I'd like to reiterate the evolution of ray tracing from considering just a few rays towards the incorporation of more and more rays in order to capture more and more visual effects. In a minimalistic setting, we would consider viewing rays to compute the light transport from the scene towards the sensor, and we would incorporate shadow rays that capture the light transport from light sources towards visible surfaces. In the illustration, we have two light sources, so for each visible surface point, we trace at least two shadow rays. If a light source is occluded by another object in a scene, then there is no light transport from the perspective light source. Otherwise, we consider the light transport from the source. In an implementation, we would generate and traverse a ray, compute an intersection with the scene, and evaluate a shading model. This shading model relies on illumination information from the shadow rays. Finally, the computed light transport along the primary ray would be stored in the frame buffer. The concept outlined on the previous slide has first been proposed in 1968, where viewing and shadow rays had been used to resolve visibility and to classify illuminated from shadowed surfaces. A rendering result from that paper is shown here on this slide. A minimal ray casting setting can be extended to recursive ray tracing as indicated here in this illustration. Now we do not only consider so-called direct illumination from light sources, but we also consider so-called indirect illumination that results from the reflection from other surfaces in a scene. The usefulness of the incorporation of the illumination from other objects is particularly obvious in the case of shiny surfaces. As shown in the illustration, it makes sense to not only use shadow rays for the red object, but also additional reflection rays. And now, in order to compute the light transport along the reflection ray from the blue object to the red one, we need to estimate the illumination of the blue object, and then we evaluate the rendering equation for the blue object. So, in order to evaluate the rendering equation for the red surface, we recursively evaluate the rendering equation for the blue object. By incorporating more and more reflection rays and also more and more bounces in the scene, the computed light transport along the primary ray gets more accurate. The idea of recursive ray tracing has been introduced to the graphics community in 1980, and here we have an exemplary rendering that shows the capabilities of the recursion concept. In particular, mirroring surfaces can be easily handled, and also transparent surfaces can be rendered by not only considering reflection rays, but also refraction rays. Now the next important development is the general incorporation of more and more rays in a computation. So we do not only use more bounces as in recursive ray tracing, but we also use more and more rays at each bounce. This is shown in the illustration. In order to compute the outgoing light or radiance LO from point P in the direction omega O, we consider larger numbers of incoming rays, and we use the transported light or radiance Li from a variety of directions omega I within the hemisphere to approximate the integral in the rendering equation. One very popular option to solve the integral is Monte Carlo integration, and the respective ray tracing variants are referred to as stochastic ray tracing. They are particularly characterized by the fact that the directions omega I are randomly sampled. And now graphics research tries to combine the randomness of the direction sampling with strategies to identify more or less relevant directions. Directions omega I where larger amounts of light Li are transported are more relevant in the computation, while directions with less light transport are less relevant. In the previous slides, I have tried to convince you that the consideration of more rays in a rendering process improves the quality and accuracy of a rendered image. This fact is shown here again on this slide. We see three renderings of the same scene using ray tracing. On the left-hand side, we just use viewing rays, and at intersections, we set a user-defined color. In the image in the middle, we use viewing and shadow rays, and we evaluate, for instance, the Phong illumination model at the intersection points. In the image on the right-hand side, we see a result where stochastic recursive ray tracing has been used, which means that the rendering equation has been evaluated at intersection points. As you can see, computing more and more light transport in a sea enables the capturing of more and more visual effects. This improves the realism and also the accuracy. On the other hand, the rendering gets more expensive. Here we have another example that illustrates the capabilities of the ray tracing concept. Basically, all material types can be handled, and reflections and refractions can be considered. Also, subsurface scattering can be added, for instance, in order to render wax or skin. By using area light sources and large numbers of shadow rays, soft shadows can be reproduced. Also, caustics, bright spots where larger amounts of light are concentrated, can be rendered. Then all types of inter-object illuminations can be handled. Sometimes these inter-object illuminations are classified with respect to the surface material. So we can have diffuse or specular interreflections. In order to capture specular interreflections, fewer rays are sufficient, while diffuse interreflections typically require more rays. Last but not least, camera effects can be modeled. So depth of field or motion blur effects can be realized within the ray tracing concept. From the concepts and from the capabilities, it's rather straightforward to derive the main challenges in an implementation of a ray tracer. The most important aspect is certainly the ray primitive intersection. We typically have complex scenes with larger numbers of primitives, and we also have larger numbers of viewing rays. So even if we would not use recursive ray tracing, the number of ray primitive tests is huge. Therefore, spatial data structures are generally used to accelerate the ray traversal. These data structures can either be bounding volume hierarchies or space subdivision techniques. And you can imagine that the complexity of the task varies with the scenario. For instance, if we would like to render a video of a dynamic scene, then the tests and also generating and querying the data structures is expensive. Another important challenge is the number of rays. We have seen that more rays improve the image quality, but still our computing resources are limited, so we need strategies that efficiently distinguish relevant from less relevant rays. And the last challenge is the recursion depth. Dependent on the visual effects that we would like to reproduce, we need more and more bounces. It's obvious that transparent surfaces cannot be rendered if we just use one bounce. Again, larger recursion depths correspond to larger numbers of rays, which is expensive. That's it about the historical rendering aspects. I've discussed the development of rasterization and ray tracing, and I've compared both concepts. In the context of ray tracing, I've discussed its evolution from simple raycasting towards stochastic recursive ray tracing. We have also seen the general capabilities of ray tracers, and I've outlined some of the challenges that we face in implementations. Now I'd like to summarize this introduction. Throughout this presentation, I've discussed various aspects that are relevant for high-quality renderings. And these aspects are actually the focus of this course. First of all, I will discuss how to work with radiometric quantities in order to describe light that moves along rays, or in order to describe the illumination strength of a surface element. Using these radiometric quantities, we will see how to describe reflection properties of surfaces. Incoming light can be absorbed or reflected, and light can be scattered in different ways dependent on whether we have a shiny or a matte surface. From the representation of the reflection properties, we get to the rendering equation that models the light interaction at surfaces. And now we are prepared to compute the light transport in a scene, which is the basis for photorealistic renderings. And here we first look at the radiosity concept, where we solve a linear system to globally compute the entire light transport in a scene. Understanding the radiosity concept is an important prerequisite in order to understand why ray tracing actually works and why ray tracing converges to an accurate image. Then we look into ray tracing, which is a huge field. We will focus on stochastic ray tracing, where we use Monte Carlo integration to solve the integral in the rendering equation, and I will introduce some basic variants of stochastic ray tracing. In this course, I will not address the problem of ray primitive intersections. This topic has already been covered in our introductory graphics course. And I will not cover spatial data structures for the acceleration of ray traversals. So the course is more focused on concepts and less on implementation details. Thanks for your attention.